Today in calculus, we're going to review the fundamental theorem of calculus one more time. We did a lot of this work already, but I think this time when we do it, we're going to have a little bit of a sharper eye as to what we're going to be seeing. And then at the very end of this, we will finally get some antiderivative rules for you to memorize. So, I don't know why people really enjoy memorizing antiderivative rules. Here you go. As illustrated in the Museum of the Rockies in Bozeman, Montana, exhibit on Triceratops growth, it's believed that the horns of a Triceratops changes dramatically as a dinosaur matures. As the dinosaurs grow, the brow horns change from a backward curving in the foreground to forward curving in the background. It's likely that Triceratops horns and its frill were used in combat against other Triceratops, as well as for visual display, mating, communicating, species recognition. The dinosaur also used its horns and its frill against its main predator, the Tyrannosaurus, which, of course, is like the battle of the millennium now, isn't it? So let's get going with our antiderivatives. Suppose that the antiderivative of f is g. So if you take the integral from constant a to variable x of ft dt, you get the function gx. We'll call that equation 1. Well, this means that g of x plus c can be used to represent the family of functions for the antiderivative of f of t. So the antiderivative of f of t is f of x, which in turn is equal to g of x plus constant. So, that's a lot of things to keep straight here. Let's just go with what we know from the algebra. We know f of b is equal to g of b plus constant. So that means fa, that should be equal to g of a plus constant. That piece of information comes from the highlighted bit over here, where capital F of x is equal to capital G of x plus constant. So capital F of a is equal to capital G of a plus constant. The next thing we're going to do is we're going to substitute in, because I know that capital G of x is the integral from a to x of little f of t. Now, there's a few things that are going to happen here. The first of which is you notice that the plus c is going to cancel. The next thing you're going to notice is that in the second bit here, this integral from a to a, that's equal to 0. So when you take all of that stuff away, you get basically the fundamental theorem of calculus, where capital F of b minus capital F of a is equal to the integral from a to b of little f of t. That is the fundamental theorem of calculus. And we know the relationship here, of course, is that the derivative of capital F is equal to little f. So all of that is stuff that we met a couple of lectures ago, a couple of videos ago, when we were talking about antiderivatives for the very first time. So as long as f is any antiderivative of f of t, then this fundamental theorem of calculus is going to be true. It doesn't have to be the exact antiderivative. It just has to be some antiderivative, which is what gives us justification to kind of get rid of the plus constants, because we can, another way of thinking about it is we can just make those constants equal to 0. Either way, at this point in your calculus, this isn't going to change much of what you do if you've been consistent in what we've been doing. So we've already used this second part of the fundamental theorem of calculus, so we're not going to go into a whole lot of problems here. We're just going to do this one. where we have the integral from pi over 6 to pi over 3 of cosecant squared x. So let's see, what is the derivative of cotangent? That is the hint. The derivative of cotangent x is negative cosecant squared x. Let's multiply both sides by -1. Now we have that the derivative of negative cotangent x is cosecant squared. All of this to say that the antiderivative of cosecant squared x dx is negative cotangent x plus constant. And now that we have our antiderivative, we can work with the integral. Evaluating the integral of cosecant squared x, we just need to evaluate the antiderivative. So we're evaluating negative cotangent x from pi over 6 to pi over 3. That's negative of cotangent pi over 3 minus negative of cotangent pi over 6. And then after you evaluate and rationalize, you get 3 root 3 minus root 3, the whole thing over 3. For the next problem, we're going to find the area of the region enclosed by the curves y equals x squared minus 1, x equals -2, and x equals 2, and the x-axis. So looking at the graph that we have here, we've got some regions where the area is above the axis, some where the area is below the axis. So if we're trying to find area, we're going to have to take into account that part of our integral is going to evaluate to be negative. So let's get started. The first area of subregion 1, that's going to be the triangular shape above the x-axis from -2 to -1. So that area is going to be equal to, and let's get our antiderivatives. Hopefully by now we know that the antiderivative of x squared is 1/3 x cubed. We've just used it so often that we just have that memorized. And then the antiderivative of 1 is x, because the derivative of x is 1. So that one is pretty easy, and when we evaluate that, I'm not going to make a big fuss about it. You're going to get 4/3. Again, I'm going to leave that work up to you. It's just some simple algebra stuff. The next region is from -2 to +1. So let's substitute things here. So we'll integrate from -1 to 1 of the same function, x squared minus 1. And actually, that's not going to be the area, is it? Because that antiderivative is going to be negative. Now, there's a couple different things you can do to make this antiderivative evaluate to be positive. I'm just choosing to put a negative sign in front of the antiderivative to make that all work. Okay, once we've done that, our antiderivative is just going to be the same antiderivative with a negative sign in front of it. And when we go from -1 to 1, we again get 4/3, which is kind of mind-boggling, really, when you think about it. Okay, that's fine. Subregion 3 is from 1 to 2, or from x equals 1 to x equals 2. So the area is going to be the integral from 1 to 2 of the same function, x squared minus 1. Antiderivative is the same antiderivative, 1/3 x cubed minus 1. And the antiderivative evaluated from 1 to 2 is 4/3. So the whole area is 4/3 plus 4/3 plus 4/3, which is just 4. Let's see if we could find units here. No, I don't see any units here, so we're just going to say square units. And that's finding area with some of the region above the x-axis and some of the region below the x-axis. So let's move on into the next part with the antiderivative rules. And, you know, in bold here it says, yes, you must memorize these. So these are the ones you have to memorize. We have met a few of these already. For example, here's constant multiple. Here is sum and difference. Most students will find this to be the most useful antiderivative of all, and it is the antiderivative for finding any power function. So let's get into it. Let's take a look at the power function. If I want to find the integral, the antiderivative of x to the 7th power, first of all, notice that the base of this is the variable, and it's the same variable of integration, x. And then the power is constant. So this is constant power, not an exponential function, a power function. And here's the rule. We're going to take the old power, 7, and we're going to add 1 to it. So 7 plus 1 is 8. So we're going to say 1 over 7 plus 1, so 1/8, x to the 7 plus 1 power, plus constant. This rule is so versatile because you can use it in places where you might not even think you can use it. For example, let's look at the antiderivative for 1 over the cube root of x. That doesn't look like x to a power, does it? Well, actually, yeah, using some algebra, you can turn this into x to a constant power. This is the same thing as x to the negative 1/3 power. And once you've seen that, then your head really starts to think about all the things that you can do with this power function. Let's complete this antiderivative. The antiderivative looks kind of ungainly. 1 over negative 1/3 plus 1 multiplied by x to the negative 1/3 plus 1. Just a little simplification and we get 1 over 2/3 x to the 2/3 power, which simplifies to 3/2 the cube root of x squared plus constant. So as you can see, things work out. Now, the one problem with the constant power rule is when you have that constant power is -1, as in the next case. Here, we have to the -1 power, and if you think about that, when you do -1 plus 1, you get 0. And in the power rule, that would be 1 over 0 multiplied by x to the 0. Now that's not going to work. So this function, the natural log function, is in some ways defined by, we know that the antiderivative or the integral for 1 over u has to exist, and it is a number. There's an area there. So let's make up a function for it, and the function is the natural log function. Now, I say just make up, but there are definite links between the natural log function and the exponential function, but it just didn't have a name. So that's where the natural log function comes from. It is that area associated with the curve 1 over x. Now, the next 3 lines here are antiderivatives that come from trig functions. And they work basically like the reverse of the derivative. So we're not going to talk too much about them. But I will say this. Notice that there isn't an antiderivative for tangent here. There isn't an antiderivative for secant. And it's not that those antiderivatives don't exist. It's that we're going to need to learn a lot more technique if we want to understand where those antiderivatives come from. So these right here are just the ultra basic trig antiderivatives. The next one over here is the antiderivative of the exponential function e to the x power. And as expected, since the derivative of e to the x is e to the x, the antiderivative of e to the x is also e to the x. Here is the antiderivative for any exponential base function, a to the u. That's going to be the antiderivative of a to the u is a to the u divided by the natural log of a. That's a handy one to have. Students who do really well, they'll remember that one. Students who are kind of middling or on the lower side of things, this is one of the ones that they don't often, that they just kind of forget about. So choose your participation here. This is the antiderivative of the natural log function. You can memorize this if you would like. We are going to go into the derivation of this antiderivative in more detail. I think that's in chapter 7. And this is the antiderivative for any log function for any base. This one does get seldomly used, so only the cream of the crop really will remember this one. So again, choose how many of these do you want to memorize. It's totally up to you. What you memorize will in some ways determine how you do in this class. And this brings us to our important ideas. And to tell you the truth, there's not a whole lot new here that we haven't seen before. I mean, we saw this part of the fundamental theorem of calculus in section 6.3. So we're just going to go right into, we should say this. Make sure you learn those basic derivatives, antiderivatives, in this page 3. So there's your caution. Check your understanding is very similar to the problem that we had. We've got a straight line road runs between two lagoons at the Triceratops paddock. If the x-axis is the road and the boundary of the lagoons is modeled by the curves y equals 4 minus x squared and x equals 3, with both x and y in kilometers, what is the total surface area of the lagoons in the Triceratops paddock? Okay, well, unlikely that we would get an actual parabola as a boundary for a lagoon, but this is just kind of approximate. Luckily for us, we're told that points of intersection here we got are -2 and +2. That's going to help us. And I think we're ready for our integral. Now the first one is we're going to integrate from -2 to 2. The area of this first lagoon is above the x-axis, so we just need to straight integrate from -2 to 2. We're going to use our newfound powers of antiderivatives, and we can say that the antiderivative of 4 is 4x. And then the antiderivative of x squared, I'll play along with you on this one. 2 plus 1 is 3. So it's 1 over 3 multiplied by x to the third power. Next task is to substitute the upper and lower limits. And then you just evaluate that algebraically. First area is 32/3. For the second part of this, we're going to we have an area that's below the x-axis, so we're going to have to find a way to make that area positive. We can definitely do it just artificially, but let's figure it out. Write down our integral. The area is the integral from 2 to 3 of 4 minus x squared, and I think I need a negative sign there. So I'm just putting a negative sign in front of the entire thing. That's going to make that integral evaluate to be positive. Just like last time, we're going to go ahead and find our antiderivative, which we know what it is already. And we're going to evaluate from 2 to 3. Substitute the lower limit and the upper limit into the antiderivative. That gives us that area 2 is 7/3. Total area is area 1 plus area 2, which is 32/3 plus 7/3, or just 13. And the surface area of the lagoon is 13 square kilometers. So I hope you feel better now that we have some definite rules for how to evaluate integrals and antiderivatives. That power rule, again, learn it. It's going to be your best friend. And then all the other rules, you really need to remember all of those. So that's it for today. See you next time here when we play with more calculus.